Hello. Hello. Good evening, everyone. This is Vaishali Chaudhary. So today is the first tutorial session of a brief introduction of microsensors. In this session, we'll discuss some problems based on electromechanical system. So we'll start the session. We'll start with some basic formulas of mechanics, basic mechanics. So first, we'll learn stress. We denoted it with sigma, which is nothing but a force per unit area, and the unit of the stress is Newton per meter square. Okay, then strain. We denoted it as with sigma, with epsilon, sorry, and the strain is a change in length to the original length, and the unit of the strain is unit. This is the unitless quantity because this is in meter and this is also in meter, so meter and meter get cancelled, so it's unitless quantity. Then we learn the famous law of mechanics, which is Hooke's law. That shows a relation between stress and strain. So the Hooke's law says that in mechanical system the applied stress is directly proportional to the strain, or sigma is directly proportional to the epsilon. If we remove this proportionality constant, if we remove this proportionality, we'll have one proportionality constant y, which is called Young's modulus of elasticity, and it shows the elastic property of material of any bar or cantilever beam. Okay, so uh, we'll give it as equation 1. So from in equation 1, if we put the value of sigma and strain, we'll get stress is nothing but a force per unit area. Y is Young's modulus of elasticity, and strain is change in length to the change in to the original length. If we solve this for change in length, we'll get F dot L by A by Y. So if in any system, if we apply a stress and you want to measure a change in length due to this strain. With this formula, you can calculate it. You can calculate S. Thus, del L is can be expansion or contraction. Right? Now, we'll move on to a spring mass system. Spring mass system. First, we'll talk about parallel system. Suppose we have two spring suspended over and fixed to the then the one side of the spring is fixed to a fixed, and the spring constant of the individual spring is K1 and K2, and we are applying a force in this direction. Okay, so the deflection will be X, because if you stretch it, it will deflect, in the direction of force, but at the same time the individual spring will force a opposite force, acting opposite to the direction of the applied force. So for spring 1, this is F1, and for spring 2, this is F2. So force, we can write it as force F1 for spring 1, F1, which is opposite to the applied force, is K1 times X, where K1 and K2 are the spring constant. Okay. Similarly, for spring 2, F2 is K2 times X, because the one end of this spring is attached to a fixed body, and the other end of the two springs are connected to a point which is common to both. So the both spring will experience the same deflection. That's why the X is same, but the forces are different. So for spring 2, the repulsive for the opposite force is K2 times X. Now, if we calculate the total force F equal to F1 plus F2. If we put the values of F1, which is K1 times X, and K2 times X, we will get K1 plus K2 times X, or we can say that equivalent spring constant in case of parallel system is K1 plus K2. So in parallel system, K equivalent is K1 plus K2. Okay. Now we will move on to a series system. We'll see what happens in series systems. Series system. So, as the name suggests, in series systems, we will connect a two spring in series. The one end of the spring is attached to a fixed point, and the other end of the first spring is connected to the next spring, and we'll apply force in this direction. So in that case, they will experience the same force, but the deflection will be changed. That spring one will experience a deflection of x1, whereas the spring 2 will experience a deflection of x2. Okay, and the time constant will be is k1 and k2. So in case of the series system, the the repulsive force experienced by, or the opposite force experienced by individual spring is same. So F1 is nothing but K1 times X1, because in this case deflection will change but the force will be same, and this is K2 times X2. Okay, so the total deflection due to the force F is x1 plus x2. X is nothing but 1 upon f upon k times equivalent. X1 is f times k1 plus f2 is f times k2. We can write it as 1 upon k equivalent is 1 upon k1 plus 1 upon k2, or k equivalent, and we can write it as in series system k equivalent is k1 times k2 divided by k1 plus k2. This is how we can calculate the equivalent spring constant in case of series system. Now we will move on to a force. Force on cantilever beam. Suppose We have a cantilever beam having a length L, width W, and height H. This is Y, this is X, and this is Z. So, if we apply a force in X direction, we'll call it as axial force. Axial force in X direction, right? This force is, for this force, what will be the spring constant? So that spring constant is K in axial direction is Y W H by L. Okay. Similarly, for Y direction, K in Y direction is Y W H cube by 4L cube, and in Z direction, spring constant in Z direction. It means in case of Y direction, we are applying a force in this way, means perpendicular to this height. So we'll cube the height. In case of Z, we are applying in the direction of width. So we'll cube the width. So this is how we can calculate the spring constant if we apply a force in different direction. Okay. So we have seen some basic formulas. Now we'll apply these formulas on some problems. So first we'll start with problem 1. So in this problem, they are giving a spring mass of 7.5 into 10 to the power minus 6 kg is attached. So this is mass is attached to two bars, both of length 125 micrometer, but the cross sectional areas is 16 micrometers square and 25 micrometer square respectively, as shown in figure. The beam material is silicon having a Young's modulus of 170 gigapascal. So we have to calculate the equivalent stiffness constant. Means we have to calculate the KT in kilonewton per meter. Okay. So the length of the each bar is 125 micrometer. Okay. This is also a 125 micrometer, but the cross sectional areas are different. This is 16 micrometer square, and for this bar this is 25 micrometer square. Okay. Young's modulus of elasticity is 170 gigapascal, and mass m is 7.5 into 10 to the power minus 6 kilograms. So this mass is in kilogram. Okay, we have to be very careful about the units. So in first part, uh, we have to calculate stiffness constant. So first we'll start with part A. If you notice carefully, the part A, we can draw a equivalent diagram like this. Means two springs are connected in series and a mass is attached to one end of the spring and the force is applied in the axial direction. So obviously, the both for two beams, the spring constant is K1, and for the other one, the spring constant is K2. Okay, so we have learned in series system the equivalent stiffness constant. Uh, Equivalent stiffness constant or spring constant of series system is 1 upon K equivalent is 1 by K1 plus 1 by K2. Okay, or we can rewrite it as K equivalent is K1 times K2 by K1 plus K2. Okay, so now we'll calculate the value of K1. We have seen if we apply a force in axial direction, then the spring constant will be y times W h by L, where y is Young's modulus of elasticity, W is width of the beam, and h is the height of the beam, and L is the length. Okay, if we put the values, y is 170 gigapascal, giga is nothing but a 10 to the power 9, h is 16, h w and h is nothing but a area, and we have given with the area of one first beam is 16 micrometer square and the length is 125 micrometer. Okay, so K1 will be 21.76 kilo Newton per meter. We will not change kilo in Newton because they were asked to calculate in kilonewton per meter. So similarly, we'll calculate the stiffness constant for second beam, which is nothing but a y. We'll write it as A2 by L2. Okay, this is 170, 10 to the power 9 gigapascal. The area of the second beam is 20 micrometer square, 25 micrometer square, and the length is same. So if you solve this, you will get a 34 kilonewton per meter. So now from equation 1, the total equivalent spring constant will be 21.76 into 34 divided by 21.76 plus 34 kilo Newton, or K equivalent is 13.268 kilonewton per meter. Okay, so this is the answer of the first question. Now we'll move on to a second part. So in second part, calculate the equivalent stiffness constant in kilonewton per meter unit for the beam dimension mentioned in part A. So the dimension of the beam is same as for previous question, previous part. If the arrangement is as shown below, beam material also as same. Means in the second part, only the arrangement is changed. Rest of the specifications are same. So if we draw a free body diagram of the second part, so we can draw it as first spring having a spring constant of K1, then one mass, then again the other spring with spring constant K2, and this is fixed. Okay, so if you noticed carefully, this is a series system, parallel system. It's a parallel system. And we have seen in case of parallel system, the equivalent spring constant K equivalent is K1 plus K2. We have already determined the values of K1, which is 21.76 kilonewton per meter, and this is 34 kilonewton per meter. So the equivalent spring constant or stiffness constant in case of B parallel system is 255.76 kilonewton per meter. Right. So this is how we can calculate the spring constant in case of series and parallel connected system. Now we'll move on to a second problem. Okay, so this the problem is a glass block of side 1 meter is Hello. So sorry guys, there was an interruption. Now again I'm going to record. I'm going to share my screen. So yeah. So the question is, a glass block of side 1 meter is dipped in the water having a density of 8000 kilograms per meter square. The surface tension coefficient of water is 0.073 Newton per meter, and they were asking what will happen to the glass block. Will it sink? And in second part, they are asking what will have to manipulate the buoyancy force acting on the block, and we have to take these 10 meter per centimeter. Okay. Now we'll solve the problem. So we have a glass, we have water, and we are trying to dip this block, which is made of a glass, having a length of 1 meter. The density is 8000 kilograms per meter square. The surface tension coefficient gamma is 0.073 Newton per meter, and the CHG is 10 meter per second square. Okay. The length of the block is 1 meter instead of 8, right? So if you notice that uh, that block, if you try to dip that block in water, that block will face a force which will downward. Similarly, while unaudible. Hello. Yes. The surface tension force will act in this direction, and the water will create a force in that direction. Okay, so first we'll calculate the downward force. Downward force, we'll denote it with FW due to the water is m times g. M is nothing but a rho L cube by g. If we put the values of rho L and g, we'll have a downward force of 80,000 newtons. Okay. Similarly, we'll calculate a upward force or surface tension force. We will denote it with F times F subscript ST is gamma times S, where S is surface area of the glass block. Okay, so in case of this square block, the surface area would be 4 times length. So if you put the values of surface area and surface tension coefficient, which is 0.073 into 4 times L is 1 meter, we'll get a surface tension force of 0.292 Newton. Okay. Now if you compare these two forces in equation A and B, so from A and B you can conclude as the downward force is too much greater than a surface tension force. It the downward force try to try we can say that in this case the glass block will be sink. Now in the next part, what it is m times g or rho L cube by g, rho L cube times g, or if we put the values of rho L and g, we'll have a downward force of 8 into 10 to the power minus 4 Newton. Similarly, we'll calculate upward force or surface tension force will denote it with FST is gamma times S or gamma into 4 times length. So gamma is 0.073 because in both the cases the surface tension coefficient is same, only the length is changed. 4 into 10 to the power minus 6. Okay. So if you solve this, you'll get a surface tension force of 2.9 into 10 to the power minus, sorry, this is 1 4 minus 140. Okay. So 2.9 into 10 to the power minus 7 Newton. Okay. We'll give it as C, equation C and D. So if you compare the equation C and D, so from equation C and D, you can notice the downward force is less than surface tension force. Okay, it means is reduced the power minus tension force will dominate the downward force. Therefore, the block will float, right? Because in second case, the surface tension force is the dominant one, so it won't allow to the block to dip into the water. Rather, it will try to try to try to uh, try to force the block to the upward direction, so that block will float. Okay. Now we'll extend this problem and we'll see what would be the critical length, because if we take the length of 1 meter, that time the up or downward force is the dominant one, but when we reduce the length to 1 micrometer, so the surface tension force was the dominant one. So now we see what is the critical length where these two forces will be equal. Okay. So now we'll calculate the critical length. Where the downward force is equal to the surface tension force. Okay. Critical length. So the downward force is nothing but a rho LQ times G, and this is gamma times S, or we can write it directly as 4 times L. Okay. So if we simplify this will get cancelled. Rho L square by G equal to gamma times 4, or length is nothing but a gamma times 4 divided by rho times G, ka under whole under root of this. So this is the critical length of the glass block where these two forces are equal, or this system is in equilibrium condition. So this is how we can calculate the critical length and the upward and downward forces acting on the glass block. Now we'll move on to our next problem, which is based on the concept that we have learned. So in this question, what is the critical length in mm for a glass cube having a density of 2025 kilograms per meter cube to just float on a fluid having a surface tension of 30 millinewton per meter? Neglect the buoyancy force acting on block. So in this question, we have to calculate the critical length, and they have given the surface tension and the density. So we'll start the problem. So the density is 2025 kilograms per meter cube. G is 10 meter per second square, and the surface tension coefficient is 30 millinewton per meter. This is milli. And we have to calculate the critical length of the block glass cube. So we know critical length is the length. In that case, the upward force acting on the block will be equal, or we can write it as the downward force acting on the block will be equal to the upward force or surface tension force. Okay, so the F will denote it as with FW and FST. Okay, we'll write a critical length as L suffix C is LQ times rho G, and the surface tension force is gamma 4 times LC. This is the surface area of the glass block, and the critical length LC is 4 times gamma times rho times G, or we can write it as 2 into gamma times rho G. Okay, now we can calculate a critical length LC of 2 times gamma is 30 milli is 10 to the power minus 3, rho is 2025, and G is 10. So the critical length is 2.43 mm. So if you solve this, you will get a critical length of 2.43 mm. Because if you go beyond this, means if you reduce the length below this 2.43 mm, then the surface tension force dominates the downward force. Okay, Now we'll move on to the next problem. So in this problem, the problem is, consider a beam made of polysilicon with young modulus of 170 gigapascal as shown in figure, and having length of 100 micrometer, width is 10 micrometer, and height is 15 micrometer. A probe mass of 50 microgram is attached to its free end and resulting in guided beam kind of motion. An acceleration is applied that is in y direction is 15 micrometer per second square, and in z direction this is perpendicular to the side of beam is 10 meter per second square. So what will be the magnitude of the deflection produced in y and z direction respectively? Here all the symbols have usual meanings. Okay, so what they have given, the length L is 100 micrometer. Okay, this is width, which is 10 micrometer, and this is the height, which is 15 micrometer. Okay, so in first question the acceleration is applied in y direction. So solution, y direction. Okay, and the acceleration in this direction is 15 meter per second square. Acceleration is in y direction is 15 meter per second square. We know what is the spring constant if we apply a force in y direction, means we are applying a force in this direction, means this is uh, parallel to the height. Okay, so the spring constant in y direction will denote it with k and suffix y is y w h cube by 4 times l cube. Okay, now we'll put the values of y, w, h and l. Y is 170 gigapascal, width is 10 micrometer, and height is 15 times 15 micrometer. So will put the values of W, H and L. Now if you solve this mathematical equation, you will get a KY of 5737.5 Newton per meter. You can check this mathematical equation whether this is correct or not. Maybe there might be some problem in calculation. Also, we know in the spring mass system, the force is nothing but a spring time constant times deflection. Okay, where x is deflection due to the applied force. Also, F is ma. If you equate these two equations, 1 and 2, from equation 1 and 2, you can write as you can equate these two forces as ky times x is equal to the ma. They have been asked to determine the deflection in y direction. So we'll denote it with x in suffix y. This is ma times ky. Okay. Now we'll put the values. Xy is 50 into the mass is in micrograms. 50 micrograms. First we have to convert these grams into kilograms. So 10 to the we have to multiply with 10 to the power minus 3. Then acceleration is 15 meter per second square and the spring constant is 5737.5 Newton per meter. So if you solve this, you'll get a deflection of 0.1 micrometer. Okay. In y direction. Similarly, we'll calculate deflection in z direction. Where the acceleration in z direction is 10 meter per second square. Okay. So in z direction means we are applying a force in this direction, means parallel to the width. So we can write it as kz in the direction of the spring time constant in the direction of z is y h. We have denoted with w, right? Yes, y h w q by 4 l q. Again, we'll put the values of y, which is 170 gigapascal, h is 15 micrometer, and width is 10 micrometer, and the length is 100 micrometer. Okay, if you solve this, you will get a kz of 2550 Newton per meter. Now the deflection in z direction is xz, and we can calculate xz as ma divided by k spring constant in z direction. If you put the values, you will have 50 micrograms. Again, we'll convert this grams into a kilograms. Acceleration is 10 meter per second square, and the spring time constant is 2550 Newton per meter. Okay. I think there's some issue in the connectivity. I'm again trying to connect it. Now I'm going to share my screen again. Okay. Now we are going to learn about different systems. Okay. So the first system is in which we have one cantilever beam which is fixed to a one end, fixed end, and the other end of the beam is free and suspended. Okay. So this system is called uh, the system we can call it as fixed free system, because one end of the beam is fixed and the other end is free. And if we draw a free body diagram in this case, so we'll represent each end with its equivalent forces. So this is beam, and if we talk about a fixed end, so this end is fixed. So that end will experience a force in each direction, in vertical direction, horizontal direction. Yes. So that beam will experience a force in vertical direction in guided kind of and in x direction. Okay. On the other hand, the other end of the beam is free, so that will not experience any force because it is always ready to move. Now we'll move on to our next system, which is fixed fixed system. As the name suggests, the one end of the system when the one end of the beam is fixed and also the other end is also fixed to the particular point. So in this case, if you draw the free body diagram, so we have a cantilever beam, and in the one end the beam is fixed, so it will experience vertical force, rotational force, and horizontal force. Similarly, the other end will also experience the same force because it is also fixed to a particular point, right? So it will experience the same force. Now we'll move on to our next system, which is fixed pinned system. Fixed pinned system. Okay. So in the fixed system, again the one end of the beam is fixed and the other end is pinned. There's a hole and this pin is fixed to the bottom. Okay. If we draw a free body diagram, of this fixed pin system, so the one end is fixed, it means it will experience all the forces, horizontal force, vertical force, and the more rotational force, but the other end is means and fixed to the point, fixed to this uh, fixed to the surface, so that surface won't allow the motion in horizontal directions. It means it will experience a horizontal force. Similarly, it won't allow a motion in y direction. But this is spin, so we can easily move the rotational motion. So this is how we can draw the free body diagram in fixed spin system. Now the other system is fixed sliding system. Sliding system. Okay. So in the fixed sliding system again, the one end of the beam is fixed and the other end can slide over a fixed surface. Now again, if we draw a free body diagram of the fixed slide system, fixed end will have all the forces: vertical force, downward force, and the other because now this other end can move in horizontal direction. Now this system can slide in horizontal direction. So in horizontal, so it will not experience a force in horizontal direction, but also that in the other hand it is pinned, so it can easily move in rotational direction also. But this sliding system won't allow the system to move in vertical direction, so it will experience a force only in y direction, because in x and rotational direction it can easily move. Now the we'll move to other system, which is again a fixed sliding system. Okay. So other is again this is a fixed sliding system, but instead of the sliding in horizontal direction, we'll have a sliding wheels in vertical direction. So now we'll have a sliding wheels. This is beam which is fixed to one end. This is pin, and now it can move in vertical direction. Okay. So if we draw the free body diagram, so for fixed end, same forces: horizontal, vertical, and sliding, and rotational. Now, in the right hand point of the beam, now the system can move in vertical direction instead of horizontal direction. So that system will experience force in horizontal direction, because now the sliding wheels in vertical direction, so it can directly move, so it can easily move in vertical direction. Also it is pinned, so we can have a rotational motion also. Only the horizontal motion we can't have this. So that system will experience a force in x direction. Now the last system, which is fixed guided system. Okay, so in fixed guided system, again the beam is the one end of the beam is fixed to the fixed, and instead of pinning, that system will have a wheels in vertical direction. Okay, if we draw the free body diagram, then to the fixed end, same forces, again same forces, horizontal, vertical, sorry, horizontal, vertical, and rotational forces. And now on the other hand, and this system is not bent, means it won't allow a rotational motion, so it means now it will experience a rotational force. Also, this wheel is placed in vertical direction, so the vertical movement can be easily happens, but it will restrict a horizontal motion. So we'll have a horizontal force and rotational force. So these are the six type of system in mechanical in general mechanical system. These are general mechanical system. One is fixed free, as the name suggests. One end is fixed and the other end is free. The other system is fixed system, then fixed pin system, fixed sliding system. We have two variant in fixed sliding system. In one variant, the wheels is in horizontal direction, and in other system it's in vertical direction. Then the last is the fixed and guided system, where the other end is not pinned, but we have wheels in vertical direction. Okay, now we are going to move towards the problem. So the problem is a folded beam, suspension of an electrostatic com drive microactuator. Below figure shows the suspension of an electrostatic com drive microactuator. Except for the darkly shaded region marked as fixed, the rest of the structure is free to move above the substrate, separated by a gap. Obtain the linear stiffness of the suspension in the vertical direction, that is along the axis of the symmetry shown in terms of the length L, in plane width is W, Young's modulus is Y, and the out of plane layer thickness is T. They have given Y is 150 gigapascal, S is 900 megapascal, length is 200 mm, width 5, and thickness is 3 mm respectively. Okay, so if you noticed carefully, this is a symmetrical structure, means the system is having a symmetry, means if you cut the system in this way, you will have two similar parts. Okay, or we can say that we have a square, uh, means we can, if you cut it in the center part, you'll have a two same portion. Okay, they are saying this darky shades is fixed end. and the force is applied in this direction. If you notice carefully, or we solve this problem, if you noticed carefully, this if we apply a force in this direction, so this point is fixed, right? Means this B and A will experience a same force. Similarly, this C and D will experience a same force. So if we draw a free body diagram of the first half side, we'll draw free body diagram. So the free body diagram is like this. This is B, A, C, and D. Okay, so first we will calculate a spring constant. Means if you in the free body diagram, this A and B spring will experience the same force parallel with the C and D. Okay, now we'll calculate the spring constant. And force is applied in y direction. Okay, then spring constant for y direction is y t w cube by l cube. Okay, if you put the values, it's gigapascal into 3 into 10 to the power minus 6 into 5 micrometer, and this is 200 micrometer. Okay, so ky is, if you solve this, you'll have 7.0313 Newton per meter. So this is an in general spring constant for a single spring, as the dimension of all the spring is same. So for A, B, C, and D, the spring constant will be same, which is ky, and the value of the ky is 7.0313 Newton per meter. Okay, now we'll calculate the equivalent spring constant. So The equivalent spring constant for A and B, we'll write it as K equivalent AB, and for B, for C and D, we'll denote it with K equivalent of C and D, and for whole, we'll denote it with K equivalent. So for K equivalent of AB is these two springs are in series. So we'll apply the formula of spring constant for the series system, which is Kay times Kby divided by Kay plus Kby. Or we can write it, because the spring constant of A and B is same, so we can write it as in any form, which is K divided by 2 or Kb by 2. Okay. Similarly, K equivalent for CD can be calculated as K dy K dy. Okay, we can write it uh, as in terms of kcy and kdy, right? Now the total stiffness constant of part 1. Part 1, which is K equivalent of 1, is a parallel combination of K equivalent of AB plus K equivalent of CD, because these two equivalents are in parallel. So in parallel spring system, we'll calculate the total stiffness constant as a summation of the individual stiffness constant, right? So we can write it as K equivalent of AB is what? Ky by 2. So this is Ky by 2, and this is also Ky by 2. Equivalent of 1 is Ky. So this is a total. So this is Ky, which is 7.0313 Newton per meter. So this is for the first part. Similarly, for second part, the procedure will be same. So we can directly write it as K equivalent for second part will be same as the first part, which is 7.0313 Newton per meter. Okay. Now the total constant of the electrostatic comb drive will be, so will be K equivalent of 1 plus K equivalent of 2. Okay. So we'll add and the total is 14.0626 Newton per meter. So this is the answer. This is how we can calculate the total stiffness constant. Now we'll solve one problem. Yes, now we'll solve one problem. So the question is, a fixed free cantilever beam is made of single crystal silicon. The longitudinal axis of the cantilever, the longitudinal axis of the cantilever point in 100 orientation. Okay, so the resistor is made by diffusion doping with a longitudinal gauge factor of 60. Okay, the L is 200 micrometer, width is 20 micrometer, thickness is 5 micrometer. Okay, if a force of 100 micronewton is applied at the end of the beam in longitudinal direction, how much will be the stress? In megapascal, and how much will be the strain? Also, the change in resistance we have to calculate. If the initial resistance R is 10 kilo, we have to calculate the change in resistance also. The Young's modulus of elasticity is 130 gigapascal. Okay. So we have a cantilever beam. Okay. This is some silicon RAM. And this is two metal wires. And we are applying a force in this direction, longitudinal direction. Okay. So this problem is based on the piezoresistive sensor. Okay. So first we'll calculate the stress. Sigma, which is force per unit area. Force area we can write it as width times thickness. So the value of force is 100 micronewtons. Width is 20 micro and thickness is 5 micro. So if you calculate the strain, you will get 1 megapascal. Okay. We know the Hooke's law. So for using Hooke's law, stress is directly proportional to the strain, or sigma is Young modulus times strain, and the strain is stress upon Young's modulus of elasticity. Okay, so strain sigma is 1 megapascal times G is 130 gigapascal. So the strain value is 7.7 into 10 to the power minus 6. This is unitless quantity. Okay. So we have calculated the stress experienced by the beam when we are applying a force in longitudinal direction and having the quantity of 100 micronewton. And similarly, we have calculated the value of strain. Okay. Now, in second part, they are asking what is the change in resistance. So this is a piezoresistive sensor. So in the property of piezoresistive material is that if you apply a force in any direction or if you stretch the material, the resistivity of material is changed. So in that case, you are applying a force in the longitudinal direction of the material, means you are stretching the material, so the resistivity of that beam will change. And they are asking what is the change in resistance correspond to the force. Okay, so in second part we have to calculate the change in resistance del R. So first we'll talk about the gauge factor. We'll denote it with G is the ratio of change in the resistance to the original resistance by strain. Change in resistance by strain. Okay. Using this formula, we can calculate the change in resistance. So in this question, they are providing a gauge factor of 60. We have calculated the strain value as 7.7 and resistance of initial resistance is 10 kilo. So from equation A, del R can be written as G times strain times initial value resistor. So the del R should be G is 60, strain is 7.7 into 10 to the power minus 6, and this is 10 kilo ohms. So the change in resistance is 4.62 ohms. It means if you are applied a force of 100 micronewtons in the direction of the length, the change in the resistivity of the material is 4.62. It means if the initial resistance of the beam was 10 kilo ohm, by applying the force of 100 micronewton, now the resistance of the material will be 10 kilo ohm plus this change delta R. Okay, this is how you can solve the problem based on piezoresistive sensor. Now we'll solve one problem again, one based on the parallel system, parallel spring mass systems. Suppose we have two cantilever beams attached to a fixed end. On the other end of the two beams, one mass is connected. The length of the two beams is same, which is 200 micrometer. But the area is changed. This guy is having 8 micrometer square and the other one is 25 micrometer square. Okay. Young's modulus of elasticity of the material is 130 gigapascal, and we have to calculate the equivalent stiffness constant. So for beam 1, K1, we'll change the color. Yes, we can change the color. So the solution is swing constant connection direction beam 1, which is y times area of A1. Let me calculate this. One 30 gigapascal and 25 . Yes, you'll get a spring constant of 162509. Newton per meter. Similarly, we'll calculate a spring time constant for beam 2, which is y A2 times L 130, and the area is 8 micrometer square. Okay, and the length is same. So again we'll calculate yes, we got 5200 Newton meter. So this is a parallel system. Parallel system. So the equivalent spring constant is Kax1 plus Kax2, which is 16250 plus 5200 Newton per meter. So the total spring constant is 16250 plus 5200 is 21450 Newton per meter. So this is the answer. Okay. So we'll summarize all the questions. First, we have started with basic formulas. We have seen stress, strain, Hooke's law, then spring mass system, and we have solved some practice problem based on this spring mass system. We have calculated the practical values of equivalent stiffness constant for the parallel system and for the series systems. Then we have solved some problem based on the critical length, or some problem based on the if we dip a glass block in a water, what will happen for different length of blocks? Will it sink or float? Okay. Then we have calculated the critical length. Then we have seen the different systems. One is fixed free, the other one is fixed fixed, then fixed pin, fixed sliding in vertical direction, then fixed guided system. Then we have solved one problem based on that. Then we have seen the electrostatic comb actuator. Then we have seen a problem based on the sensor. Okay. So this is for today's session. We have solved some problem based on electromechanical system. So guys, if you have any doubt and any queries, you can ask me or you can drop me an email. My mail ID is Vaishali VAISHALI 22 @isurb.ac.in. So you can drop me an email also. Thank you guys.